So let me first define a cross ratio. Okay, so this cross ratio of 4 points z1, z2 and z3 is defined by z minus z1, z2 minus z3 over z minus z3, z2 minus z1. Okay, you can define there are different cross ratios, but we will define the cross ratio in this way. Okay, so it is easy to remember because it is z minus z1, then z2 minus z3, so it is z1, z2, z3 in that order, and here in the denominator we have z3, z2, z1. Okay, so this is a cross ratio of 4 points, this one. And so you can check how many different cross ratios are there. All right, for example, you can change this to z minus z2 and z1 minus z3, etc. Okay, so in that way also this cross ratio can be defined. Now there is a unique Mobius transformation, that transforms three distinct points z1, z2, z3 in the z plane onto three distinct points w1, w2, w3 respectively in the w plane is given by the preservation of the cross ratios. That means w, w1, w2, w3, this cross ratio is equal to z, z1, z2, z3. Okay, so you see that, so that is what this cross ratio we already know how we define: w minus w1, w2 minus w3, w minus w3 and w2 minus w1. Okay, and this is z minus z1, z2 minus z3, z minus z3 and z2 minus z1. So this cross ratio is preserved. If this is preserved for these three distinct points z1, z2, z3 in the z plane. Z plane means it is finite z plane. Onto three distinct points w1, w2, w3. This z1 is transformed to w1, z2 is transformed to w2 and z3 is transformed to w3. These z1, z2, z3 are distinct, and similarly w1, w2, w3 are also distinct, but they may be equal to this, any one of them. Alright, that may happen, but z1, z2, z3 are distinct, and w1, w2, w3 are distinct. So this is the unique Mobius transformation that transforms three distinct points into three distinct points. Okay, so first of all you need to show that this is a Mobius transformation. In fact, this can be reduced to what, in the form, if I simplify it, you will see that this is a of wz plus b of z plus c of w plus d equal to 0. Right? And here your AD minus BC will not be equal to 0. Why? Because if AD minus BC is equal to 0, then this becomes a what? Constant transformation that we already have seen. But this is not a constant transformation because Z1 is transformed to W1 and Z2 is transformed to W2, distinct points, and Z3 is transformed to W3. So it is not a constant transformation. So I can reduce these to in this form, and this is a Mobius transformation because we have already seen that this is an equivalent form of the Mobius transformation. So therefore we have seen that this preservation of cross ratios gives a Mobius transformation. Right. Now we will show that your Z1 goes to W1. Okay. So let us show. So here, if I put Z equal to Z1, then on the right hand side you will see that this is 0. Okay. So this will imply, so that is 0. So your numerator will be 0. So we'll have that because W2 is not equal to W3. So your W will be what? W will be W1. Okay. So Z1 is transformed to W1. Similarly, if Z equal to Z3, then you will see that from here, if Z equal to Z3, then the denominator is 0. So here this is 0 because this is not 0. So I must have what? W equal to W3. So Z3 is transformed to W3. And when Z equal to Z2 in that one, so you will see that W minus W1, W2 minus W3, and W minus W3 and W2 minus W1 will be equal to, so here your Z equal to Z2, so equal Z2 minus Z1, Z2 minus Z3, and here Z2 minus Z3, Z2 minus Z1. So those will be cancelled out. So this is 1. Alright, and so you see that this becomes W minus W1, W2 minus W3, and equal to W minus W3 and W2 minus W1. And you will see that this implies that W2 equal to W equal to W2 is the unique solution of this. You can simplify it, and if I put W equal to W2, and so this is satisfied, and this is just a linear equation in W, so W equal to W2 is the only solution. So you see that Z equal to Z2 goes to W equal to W2. So therefore we have seen that this is, first we have seen this is a Mobius transformation, non-constant, it is not constant, and Z1 goes to Z2, W1, Z2 goes to W2, and Z3 goes to W3. So this is a Mobius transformation that transforms three distinct points into three distinct points. And next we are to show that this is a unique Mobius transformation. Okay, so there is only one Mobius transformation of this kind. Alright, that transforms three distinct points into three distinct points. So in the next video I will show that.